All right, guys, this is still section 6.1. This is our third video on this lesson. So if you have missed the first two lessons or one of those, make sure that you go and view those. In the first one, we talked about what vectors were and how we denote them and find the magnitude. In the second video, we did some vector operations. And we talked about unit vectors, how to find direction angles. So definitely check those out if you've missed something. This is our third and final video for this topic on vectors. Okay, so let's just jump into it. So first thing I've got on here is just kind of some definitions for velocity and speed. We've talked about the fact that speed is a magnitude calculation before. So we kind of use that in a real world example that we had talked about in class with cars going down the road. The speed that they're going, that's the magnitude that you would reference. It's not the distance that they travel. It's the speed that they're going that you use. Even though we show it with the length of an arrow, its magnitude is really more of like a speed or some sort of force. Now, that's that definition. So velocity is actually a vector because that has both magnitude and direction. And that magnitude of the velocity, that's the speed part of it. Okay. Now, that is if you end up with word problems that deal with velocity and speed. The word problem I have here, just because the it was less to write, doesn't end up using exactly velocity or speed, but just know that if you see a word problem with those words, that's what that's talking about. It's also important that we see other forms of magnitude as well. And so what you're seeing in example 7 is us seeing a magnitude, but in a weight. So you see they said a force of 30 pounds. It just keeps the box in the picture from sliding down the ramp that's inclined at 20 degrees. And they said, find the weight of this box. Okay, so I'm going to mark a few things in pencil just because I want to be able to erase my markings off of this picture. And then I will show you the math behind it kind of over here. But yeah, what we have here is this interesting little picture. I'll zoom in a little bit in case you're having trouble seeing that. So this is the picture that I've got going on. We've got this ramp that's 20-degree angle. We've got this box on top of that ramp. And the box, it says that we've got this force of 30 pounds. And this 30 pounds is just barely keeping the box from sliding down the ramp. So what we can say is that this force that we have going on right here for the box going down the ramp here, that's 30 for that magnitude. Okay, so I know that that's marked really light. Ooh, I had some white out on here and that's not wanting to go away. But yeah, so the 30 is that magnitude of that force of that box trying to go down the ramp. But it's not going. It is just got that force kind of pushing on it due to gravity and the weight of the box. Okay, now, really, initially, our scenario would have just been we have this box sitting on a ramp, right? But we have to think of the things that are pulling on the box. Yes, we have this magnitude here that's pulling 30 pounds down the ramp. But we have this downwards, like straight downwards pressure of gravity. And so that's why we see this ray that I've drawn from A to B. And we also have this weight of the box and the weight of the box is really what we're looking for as far as AB is concerned. So that's what we're going to be looking for is that weight of that box that's pressing straight down, because that's going to be the actual true weight of the box. And we also have this pressure over here that we can represent from C to A. Okay, so it's helpful to add these extra rays in here. And the main reason is because that way we're able to kind of add to our picture and kind of draw some extra parts. Okay, So the idea, they said that we're supposed to be figuring out the weight of this box, meaning I really need to figure out what this little what this vector, sorry, AB, my brain's not working yet. I haven't had coffee today. So what this vector from A to B, what is that? Because that's going to give us the weight of that box, pressing straight down with that gravity. Okay, so this might feel a little bit weird as to how I'm going to go about this, but what I'm going to do is I'm actually going to connect and make a straight up rectangle. Again, I'm kind of marking this lightly because I want to be able to erase it, especially on this whiteout part that doesn't want to erase later. Okay, but if I connect this, and let's say that I was able to connect it and make a, I can't draw, guys, but make it a perfect rectangle. So we've got right angles in the corners, right? If that's the case, then you have to remember some properties from geometry about like how some of these sides are going to relate. This AD, remember how we said that magnitude was 30? Okay, and that denotes the length of a vector. Well, so is this one down here. That's also going to be 30 pounds acting for CB. And this is where we're really going to bring some trig into it, okay? If we bring some trig into this, we're going to be able to set up a problem where we can say, if I want to find the length of AB, we have this little right triangle right in here, okay? Because assuming that this is truly a rectangle, this is a right angle. And so what we can do is we can say, okay, well, I have this little right triangle where I've got 20, I've got 30, and I need to find this missing side. And there's a trig ratio that I can use, opposite over the hypotenuse. That would be using sine. So I'm going to use, got my other piece of paper here. It's a little curled up. But we're going to use this little piece of paper here for me to write on because I don't want to write all over my empty notes more than I have to. Okay. So here we go. We're going to set up a trig ratio here. We're going to say sine of that 20 degrees. Remember, that's this angle right there. That's going to equal opposite over hypotenuse. So that's going to equal the magnitude of CB, and I'm just going to draw that for right now. Again, I'll put the number in there in a second. Magnitude of CB over the magnitude of AB. And remember how I said magnitude of AB is what we're really solving for, because that's going to give you the weight of that box. Okay, so this is just us going on a little journey to solve this part. I can plug in place of CB, since CB is also 30, I can say that that's 30 pounds. And then that really is leaving me with just one variable to have to solve for. Okay, so if I were to try to solve to get AB by itself, then we have this method where you can multiply both sides by the denominator and then divide by sine of 20. Essentially, that little shortcut that we had was that these guys kind of trade places. Which I know sounds a little bit funky, but when you do the algebra, that is what happens. So we can use that little shortcut. And then this part is what I would just type in a calculator. You would end up getting that it is about, and estimating, it's going to be about 87.714 pounds for that box. So the most complicated part of this problem is setting up this picture for this scenario, right? And if you can get that little picture set up, then you are pretty well set, I think. So, all right, y'all, let's look at this other concept, okay? I think the rest of this is going to be a little bit more simple. We've got this concept of what's called a dot product. It is a way to multiply vectors. Technically, there are other ways to multiply vectors, and each one can be used in different circumstances for whatever is the most beneficial. But the one we're going to focus on for this class is just the dot product. I'm not going to worry about the other ones right now. And so the dot product is also called the inner product. And the way it works is if you were to do the dot product of two vectors here, what happens is you just multiply the horizontal components and then multiply the vertical components, and then you just add them together. Okay, so that's the dot product. It's not super duper complicated, just another property to remember. And the dot product itself has a bunch of different properties that you can follow to make it simple to solve. So if you ever see that you have a dot product of two vectors, you can actually change the order. They are commutative. And this is a fun one down here. If you've got the dot product of like a vector to itself, then that's actually going to be equal to the magnitude squared of that vector. So that's something we'll actually use in a minute to find the length of a vector using the dot product, which is pretty interesting. If you were to use the dot product with the zero vector, it's going to result in just a 0 as your answer. Another fun thing about the dot product is it's always going to result in just a scalar or just a real number. It's not going to result in a vector. Okay. We also have, what if you were to have a vector that has got a dot product of a sum of vectors? Okay, a dot product of a sum of vectors is basically just distributive properties. So the distributive property does apply to the dot product, just like it does with normal multiplication. This one is just showing it that it can work even if the value's at the end. It does work the exact same way, essentially because it is commutative. And then we have the scalar with the dot product. And again, you're going to see like a little, the commutative property where you can kind of change the order. So C could go with V instead. So you're seeing that over here. Or you could do the dot product of U and V and then multiply it through by that scalar out there. So you can change the order and it's all good. Now you're going to see some other things here as we go through some examples. But those are some really big properties that we like to use to kind of make the problems easier to solve. Okay, but really what I want to focus on for just a moment is just getting the dot product in the first place. So that's what you're going to see in these examples. All right, so example A, we are going to follow the property that you're seeing right here at the top of your screen for our dot product. So if I find that dot product, what I'm going to do is I'm going to just multiply the x coordinates, or not x coordinates, but the horizontal components. 3 times 5. I don't need the, I swear guys, I should have drank coffee before I made my video. I'm really tired. Okay, so we have 3 times 5 plus, and then we want 4 times 2. It's not in vector component form anymore because using the dot product, it doesn't stay in vector form. You're taking the different components and you're going to result in a scalar. So this is really 15 plus 8, which happens to be 23. Ta-da! All right, look here at B. That's as simple as it gets, guys. I mean, dot product is not meant to be something crazy complicated. Okay, so the way we're going to do this, 1 times a negative 4, and then negative 2 times 3. So that's a negative 4 minus 6, which is negative 10. All right, now this might feel really gross. Okay, what you're seeing here is you're seeing like rounded parentheses on purpose. That was not a miswrite for me. That was the way it's supposed to be. And what we have is we have a difference of vectors with a dot product of a difference of vectors. And so what I want to point out is, number one, the distributive property applies the same way that it would with like FOIL here. So if you were to go through and actually full out distribute this through, you would be like foiling it. But I will tell you that it's a mess to do it in that way, especially when you don't know what I and J are as vectors. So what I'm going to do is give you a little shortcut. And that shortcut is to treat it exactly like these other problems. Okay, so there's a shortcut to getting this where you can actually get the value even though you don't know what I and j are. And that shortcut is to just treat it like that typical dot product. So what we're going to do is we're going to take 2 times, so this number here, times 3. And then we're going to add a negative 1, right, times a negative 5. And this actually gives you the answer. It's like a little shortcut so that you don't have to go through a big, fat, complicated process. Ta-da! We get 11 for that. Even though, and that, finding it any other way, that would have been a nightmare. But this does have a little shortcut property we can use like that. Okay, example 9. This is where I was saying a minute ago. We're going to use the dot product to find the length of a vector. Now, we have a property that we're going to be able to use here because really with dot products, we need to have 2 vectors to actually do that product with. And I see 1 right here. So I've got to figure out how am I supposed to be using a dot product to find that length. I'm going to go back to show you, point out one of these properties that we're going to use. You see property number 2 that has the magnitude on here. Remember that magnitude is the length. And if I were to just take this property and rearrange it a little bit, if I were to square root both sides of it, I would have that the magnitude was equal to the square root of the dot product of that vector to itself. Okay, so what I'm going to do is I'm going to make a little note here just so that we have this and you can remember where we got it from. Okay, property 2. Property 2. Okay, we're going to use that. And what I want you to remember is that I can manipulate that. I am allowed to do that. If I were to square root both sides, I would see it have the absolute value, not absolute value, magnitude. Oh my gosh. Magnitude is the square root of u and u with this dot product. Okay? And since we have that, this is something I can get the dot product for. So I'm going to do 4, negative 3, and then 4, negative 3. If we find the dot product of these two, then what we're going to do is get 4 times 4 is 16, okay, plus negative 3 times a negative 3, which is 9. That's going to give me the square root of 25, which happens to be 5. That's the length of that vector. Now, I know we have other ways, like a shorter cut, to find the magnitude there that we've learned in the past, but this does work. So it's kind of a cool trick that you can use for the dot product. Okay, and last but certainly not least, remember that term perpendicular from geometry? Perpendicular means that they make a right angle. So the idea here is they said the vectors u and v are going to be perpendicular if and only if their dot product is 0. Okay, so if you do the dot product and you get 0, that means that they are perpendicular to each other. Something that the dot product is good for is helping you to determine how, like, close to the same direction are they going to go. So, like, if you had 2 vectors that are going to go, like, really close to the same direction, they're going to have a high dot product. Whereas if you have ones that go like different directions, they're going to have a low dot product. That's something that dot products are used for, is to kind of determine like how close to the same direction are they going. And so the higher the dot product, the closer to the same direction they're going. The lower the dot product, the more opposite they are. So it kind of, or not just opposite, but also just like the further away from, opposite directions, and it could be, larger and things like that. So anyways, to tell if they're perpendicular, their dot product would be in between positive and negative. It would be 0. So that is used to help determine if you have right angles in those vectors. So, okay, prove vectors u and v are perpendicular. Like I said, this is our last one, last but not least, and let's do it. So they said we want to do the dot product of u and v. If we do the dot product of u and v, then, and we get 0, then that means that they're perpendicular. So let's do that. We're going to do the dot product of u and v. So that's going to be u, which is 2, 3, and v, which is negative 6, 4. So when I do this, I'm going to do 2 times a negative 6 plus 3 times 4. 2 times negative 6 is negative 12. 3 times 4 is a positive 12. And we do indeed get 0. Therefore, they are perpendicular. Okay? All right, guys, that is it for this section. We're just kind of trying to keep it as simple as possible. It is not technically something that is tested on the AP test, but again, it's something we should cover because you should have seen it at least a little bit before y'all get to calculus. So, all right, I will see you guys in the next section. Good luck. Bye.